So now that we covered a basic form of self-attention to understand the underlying concepts, let's now introduce the self-attention mechanism with learnable weights. So in self-attention we have these three basic steps where we compute the similarity scores, normalize the similarity scores, the attention weights, and then we compute the context vector as a weighted sum using all the inputs together with the corresponding attention weights. So now we are going to introduce a self-attention mechanism with learnable weights called scaled dot product attention. And this scaled dot product attention mechanism is the most widely used form of self-attention. So for this we are going to introduce three weight matrices. We call them UQ, UK, and UV. So the weight matrix UQ is used to compute the query sequence. So if we have an input xi, we use UQ to multiply it with xi to obtain the query. And in a similar way, through matrix multiplication, we can then also obtain the key sequence. And again, the same is true for the value sequence, where we now use the matrix UV. So where do these terms come from? So query, key, and value are actually inspired by databases. So for example, if we enter a query, the query is then matched against the key and we receive an output value. But again, the same concept applies here, the same concept that we introduced in the previous video. Namely, it's all about obtaining these context vectors. So suppose we have an input sequence of length t here, where we are showing the first, the second, and the last input element. So for each input, we then use these three matrices to obtain the query, the key, and the value sequence. So for this example, suppose we are interested in computing the context vector for the second input element. So as a first step, what we do here is we take this second query value and multiply it with all the different key value sequences here. So this will give us the unnormalized attention scores for each of the input elements with respect to the second query. Then, similar to before, similar to the basic self-attention mechanism, what we do now is we take these unnormalized attention scores and normalize them using the softmax function. And yeah, once we have these attention scores specific to the second input element, we can compute the context vector by computing the weighted sum over the inputs, where the weights here are the attention scores. But yeah, let's emphasize again that this is very specific to the second input element. So this context vector we created is the context vector for the second input element. Now, if we would want to compute the context vectors for the other input elements, we would have to carry out the same computation, but then of course switching out the query. Okay, so let's summarize what we have just seen. So for each token in the input, when we compute the self-attention, what we do is we compare that token to each other token in the input sequence. Then we compute the attention scores that are unique to that particular input token, which we also call the query. And then as the third step, we calculate the weighted average of all the inputs using these specific attention scores. So for simplicity, in the previous slides, we only focused on one token as the input, which we called the query. But of course, we would have to repeat that for all the other tokens. So in other words, self-attention is a sequence-to-sequence approach, taking n tokens as input and then returning n tokens as output. In this video, we covered the scaled dot product attention mechanism, which is a specific form of self-attention. However, notice that when we take a look at the original transformer architecture, it actually says multi-head attention. So what is multi-head attention? That's actually the topic of the next video.